formative seminar today. Just a reminder, as all the seminars for our attendees in Zoom, please keep your microphones muted during the presentation and just mute them to ask questions during our Q&A. We'll be recording this session, so everybody will be able to view it on our department YouTube channel. Our presenter today is Joe Chuba. Joe is in his fourth and final year of his PhD at the Colorado School of Mines, and is a member of the Kroll Institute for Extractive Metallurgy. He completed his Bachelor in Materials Engineering at Purdue University in 2018. His research as part of the Department of Energy Critical Materials Institute focused on recovery of critical metals, critical elements as byproducts from the Rio Tinto Connecticut copper operation. During his PhD, he has worked to evaluate methods for dust processing and with a focus on identifying outlets for recovering tellurium and indium as byproducts. So Joe will be talking to us about critical elements from copper flue dust. Thank you so much, Joe.
Thanks, Alejo. Very strange to be the one giving the presentation. Let me share my screen here.
We already did that with the flash presentations.
So let's see. Thank you again for the introduction, Alejo. As he mentioned, I will be discussing critical element recovery from copper flue dusts. My project is sponsored by Rio Tinto Kennecott, as well as the Critical Materials Institute. If I can advance the slide. There we go. So first off, I want to define what a critical mineral is. We talk about it a lot, but I don't know that we all have a very clear understanding of it. The USGS definition, which also is the US list of critical minerals, is a non-fuel mineral or mineral material essential to the economic or national security of the US and which has a supply chain vulnerable to disruption. So there's two important components here: that it's essential to economic or national security, and the supply chain is vulnerable to disruption. Copper is produced at several locations throughout the US and is very important to the economic and national security of the US. However, it's deemed not vulnerable with regard to its supply chain. So it's not on the list, even though it is quite important. Let me move my face. So what makes supply chains vulnerable? A lack of domestic production. A lot of production is moved overseas. You're all mining engineers, so you're more than aware of this. There are limited sources of them, meaning they can only be produced in isolated locations or as byproducts. Dependence on byproduct production means that if primary metal production comes down, the byproduct also will produce less. Additionally, rapid demand growth from certain sectors can lead to people buying up all of a certain mineral for a certain application, which I'll give an example of here shortly. And that can disrupt typical supply chains for other industries. Here, I'm using tellurium as an example. You see in 2011, there was a major price spike as First Solar began or continued to produce cadmium telluride photovoltaics. Tellurium is also used widely in thermoelectric devices, and all of this led to substantial increases in consumption. And that whole time, there was no significant increase in tellurium production, as it's produced primarily from anode slimes. So what ended up happening was tellurium is used as an alloying agent in metals, but the price no longer justified its use, so that consumption went down. Additionally, thin film layers got thicker and thicker using less material, even though efficiencies continued to rise. And what ended up happening was the price leveled out. That doesn't change the fact, though, that people were very concerned about price at this point, and it's representative of potential supply disruptions. Another thing with regard to byproduct production that I want to emphasize in this talk As an example, according to Rio Tinto's public publications of production, lots of P's there. They produced 40,000 tons of refined copper in the first quarter of this year. According to USGS of their tellurium production, which they recently began, they produced about 5 tons. That's $360 million of revenue from refined copper and $340,000 from tellurium. So when we talk about producing more tellurium, how much economic incentive is there to produce it on its own? That's not to say byproducts don't have major economic factors. Gold is also produced in this operation. And as we all know, gold can be worth quite a bit of money. What I want to focus on here is the fact that since copper is the primary mineral produced at this site, this is a general flow or Sankey diagram, not specific to Rio Tinto. But you'll notice as copper comes in through flotation, it then goes to smelting, converting, and fire refining, which are all pyrometallurgical processes that take copper concentrate that's roughly 25% copper and bring it to blister copper that's over 98%, well, including fire refining, anode copper, which is over 99% pure. The thing I want to draw your attention to, though, is the recycled dust and slag streams, or specifically the dust and slag streams where copper can leave the system. They're reprocessed into recycle streams and re-entered into the circuit. Additionally, the electrolyte bleed and anode slimes, copper is also recovered and not lost. Meaning this big line here, forgive me folks online, I don't know how to do the pointer, so a substantial amount of electro-refining or the copper is recovered through electro-refining, the electrolyte, and the anode slimes, and very little losses occur from what comes in the concentrate. And keep that in mind when we go to tellurium. So you can talk about abundant tellurium within the ore body, but what you really need to talk about is the tellurium you could actually produce as a byproduct. Around 90% of tellurium is lost just in flotations because it's mixed with minerals that aren't valuable for recovery of copper on their own. So immediately you've lost almost 90% of tellurium present. So if you're looking at a report of the site based on the ore body, you can't use that information to tell you how much tellurium you can produce. You need to actually look at how much tellurium can be produced based on how it moves through the flow sheet. In the end, you'll see that roughly 2% of tellurium that makes it to the concentrator gets recovered. And this is because there's not as much of an economic incentive to process in the tailings. Because although there is work being investigated using bioleaching on tailings, it just try to emphasize the fact that this is a copper mine and their goal is to produce copper. So this is what ends up happening, and they do produce tellurium. So just to reiterate, I don't want to go over your time. The element that's in the ore body with regard to byproducts in particular is not equivalent to elemental recovery, and valuations based on that is not accurate. Additionally, byproduct economics follow different rules than primary metal economics, and interest in these operations is different. In this case, less than 1,000th of the value of refined copper was represented in tellurium. Also, feel free to interrupt with questions. Don't know how much time we'll have at the end. Lastly, byproducts must be recovered where it's profitable. These are businesses and they need to make money. So just because it's there doesn't mean you can economically refine it. And I have the definition for an ore. So the difference is ores are naturally occurring versus byproduct streams. But otherwise, to process a material, you need to be able to make profit from it. So this brings me to my project. The goal is to locate and recover indium at Rio Tinto Kennecott copper operations. As a little bit of background, the majority of indium is produced as a byproduct of zinc, but it is also produced as a minor byproduct of copper. An early study at Rio Tinto Kennecott found indium within their ore body, and they tasked us at the Colorado School of Mines with recovering indium, with identifying it in their flow sheet and then recovering it. So a little bit of background on indium itself. There are no primary ores of indium. It's exclusively recovered as a byproduct and follows those byproduct rules that I have mentioned. Additionally, indium is not well documented in many metallurgical processes, so there's less knowledge on the element. I want to draw your attention to indium compared to silver. It's 10 times more common in the crust, yet 20 times more silver was produced in 2021 than was indium. So how do we address these shortages? Since there's no primary ores, we can recover indium from concentrated process streams where it is enriched to be profitably extractable. Additionally, we had addressed the byproduct economics by overall improvements to process, by treating impurities and adding value beyond just the value of the critical element recovered. And I want to emphasize that there has to be a competitive rate of return. A copper operation could improve their recovery at their smelter by reducing copper deportment to the slag ever so slightly and see a giant benefit from it. So if you compare that to recovering indium, they have to be motivated by the profit opportunity to invest new money. It can't just be a marginal profit, it has to be competitive with their other work. And then lastly, and kind of obviously, we can assay indium throughout and then report it so that other operations can also learn from this. How familiar are you all with indium? Who here has talked about indium in any context before? Lee? All right.
It was impurity in our concentrates.
What was the material you were processing?
It was a copper zinc deposit.
Okay.
And some anomalies we had.
Where was it? Can you say? Peru? So you'll see here, we're looking for indium in a copper deposit, and there's two sources in literature. There's the Kid Creek smelter and the Shenyang smelter in China, and they're both copper zinc deposits. So it's interesting that you say that. In addition to looking at the flue dust, however, we characterize 19 different streams throughout the process to identify how indium flows. Here you see a flash smelter, like the one used at Rio Tinto, Kennecott. The concentrate comes in here and then leaves through the dust. After our survey, we did find indium concentrated within flue dusts. Now we have to figure out how we're going to recover indium from the flue dusts. So the way dusts are generated, oxygen enriched air and the ore comes into the smelter. And it's a heavily oxidizing environment with high gas flows, which leads to considerable formation of dust. 5 to 10% of the mass concentrate ends up in the dust. First, there's a waste heat boiler, which cools the off gas and dust to 500 to 350 degrees C, where it then enters an electrostatic precipitator, which cleans the gas a little bit more. The SO2 is then recovered in an acid plant. So I'm focusing on the electrostatic precipitator dust. This graph here shows the different phases change throughout the waste heat boiler, and they continue to oxidize in this environment. What leaves the waste heat boiler is approximately what enters the ESP. And you can see from these phases that it should be relatively simple. Unfortunately, it's not. This image in the bottom left shows numerous different elements present, and don't try to read the table. The point is there's a numerous non-stoichiometric phases that contain various elements, making it a challenging material to process. The image here, most of you are probably familiar with automated mineralogy. The average particle size is roughly equivalent to that of a red blood cell. So it's a very fine particle. So what are the options for processing dust? Dust needs to be processed because it contains a substantial amount of copper. However, there are impurities in dust that can lead to buildup of negative elements. If dust is directly recycled to the smelter, as is often done, it leads up to a buildup of particularly bismuth, which is deleterious or it has negative effects during copper electrorefining. Its electrochemical potential is close to that of copper, and it's a severe impurity find in cathodes because it negatively impacts conductivity. It severely negatively impacts the conductivity of copper, and as we all know, copper is the conductive material. Alternatively, you can throw away the dusts, but this leads to substantial losses of copper value, and at a copper plant, their facility, they're not inclined to do that. This leaves metallurgical processing for removal of impurities while also recovering copper present. See if it'll move. There we go. Okay, so here you see a pie chart of the relative value contributions of the different elements present in dust. Really, all I want you to notice is that it's almost entirely copper, and then there's this tiny sliver in this top corner with 5 different elements reflected. My goal is to recover indium, which is the smallest sliver that you can barely make out. It's less than 1% of the total value in the dust. By now, it should be apparent that when they process the dust, the main goal is going to be to maximize recovery of value. So dust processing needs to focus on copper recovery. Second, the copper needs to be separated from deleterious elements. I've mentioned bismuth in particular, but arsenic and lead can cause issues in copper processing, and their removal is also beneficial. Then, hopefully, the developed method also provides a potentially even further enriched stream of indium for recovery. This work was conducted using literature review, experimental testing, obviously very common. Computer modeling also contributed to experimental testing to minimize the number of steps. Once you see the flow sheets, it'll be more clear why targeting experimentation was so important. Who here's heard of ETSIM? Yours? Have you? Alejo? Okay. So ETSIM is a process modeling software. It's specifically designed for mining and metallurgy. It performs mass and energy balance, so you can track streams, both elements and minerals throughout your processes. This is also very useful for flow sheet design, which you'll see in this presentation. And another factor which I will use ETSIM for that I haven't gotten to yet is that it facilitates capital and operating cost estimations. How do I hide this? Do you guys know?
You want to tell the video panel.
The video panel?
Yeah, click on more.
Okay.
And then it says hide video panel.
Video panel. Hide video panel. Perfect. Will it go away on its own?
I think you have to click away that chat.
Oh, not video panel. Floating media.
Flows.
Okay, here you see what I refer to as the water leach flow sheet. This is based off of an old published version of the Rio Tinto Kennecott Hydromet dust processing plant. One change I made, however, was that I used sodium chloride along with the acid leach to solubilize lead. Here is the ETSIM model for this flow sheet. In this format, it probably looks a little bit intimidating compared to the flow sheet. However, hopefully you can imagine that I could click on stream 12 here and I could see the mineral composition, both aqueous and solid, and then also the elemental composition of that stream. You can do this throughout the entire flow sheet, and it forces you to make your mass balance add up or lead to buildup streams. I won't spend too much time here since it is probably hard to see. Here is a novel ammoniacal flow sheet that I developed as an alternative to the previous method. The major difference here is that ammonia versus water is used in the first stage of leaching. Ammonia is very selective for copper, particularly basic ammonia, as is the case here. And here is the ETSIM flow sheet once again. Here, I want to draw your attention to stream 6, which is in the center. Right here, this is a split between the copper recovery section and then the acid leach section. And this prevents massive buildups of recirculating loads within this method. So, as I said, the goal of flue dust processing is for copper recovery, selectivity against deleterious elements, and then indium recovery. So I'll skip to the results. Here you see an elemental deportment diagram, also known as the elemental distributions. I want to mention that the water leach naturally forms an acid, roughly a pH of around 1. There's a lot going on here, so I want to highlight for you the copper recoveries. For ammonia, the copper recovery was around 70%, 71%, whereas for water leaching, roughly 60 to 65% of copper was recovered. This means that ammonia leaching did result in better copper recovery. Next, here are a number of deleterious and then just burdensome metals included. Arsenic, lead, and then bismuth all had higher recoveries in water leaching as opposed to ammoniacal leaching. Bismuth was ever so slight, so the process improvement has to be weighed on economic benefits. Another thing I'll mention is that iron, while not deleterious, just results in extra material having to be processed. But to get back to critical elements, in the first stage water leach, 18% of indium reported to the leachate, whereas in ammoniacal leaching, none of the indium was leached with ammonia. In the second stage, 30% of the indium combined leached during the sodium chloride sulfuric acid step, whereas for ammonia, 48% was recovered. If you notice, 30 plus 18 is 48%. This means that indium that was leached during the first stage of water leach, but not ammonia, all reported to that same leachate, and both resulted in relatively similar residues. But the question is, does it matter that the streams split? Obviously, we're trying to create a concentrated stream for recovery. So let's look at the flow sheets. Here's the water leach flow sheet. 18% of the indium was leached during water leaching. This is passed through a sulfide precipitation step, and then this sulfide is returned to the smelter. According to thermodynamics, the indium should precipitate along with copper and is therefore just returned to the smelter and not recovered. The other 30% that's leached during acid leaching first goes to partial neutralization. If it's precipitated during this step, it would be separated out as tailings, but if it is leached, it goes once again to the copper sulfide step. According to thermodynamics, indium should also precipitate during this step, meaning it's separated from, it's separated from the other streams, and none of these are enriched in indium. Now let's look at ammonia. Following the ammonia leach, all of the indium reports to the solid because none is leached during the first stage. Then during sulfuric acid sodium chloride leaching, around 50% of indium is leached, which is then sent to a similar step to partial neutralization you saw previously. Sodium carbonate as opposed to calcium carbonate is used here to prevent calcium from forming gypsum. For those of you unfamiliar, calcium forms, when it reacts with sulfate, forms a relatively quite insoluble species, gypsum, which is a good way for removing sulfate, but in this case, we don't want to dilute a potential product. To reiterate, that 48% of indium is expected to precipitate along with lead and bismuth, creating an outflow for the indium present. So just as a recap, we wanted to do an overall improvement, which included copper recovery and selectivity, both of which ammonia performed better than water, although the economic merits of that improvement still have to be considered. Additionally, indium recovery did provide a potential outlet for indium, although further work needs to be completed on recovery of indium itself. So let me move this. Just bringing this back to byproduct economics. This byproduct stream here, of which indium is roughly 25%, is worth roughly $1 million a year. Compare that to $1 billion operation, and it also needs to improve copper production. Based on the proposed flow sheet, both of those objectives were accomplished. Now the question is economics and the actual production of a critical element. Further work needs to be done to recover indium from this byproduct stream, although it's enriched and we're one step closer to solving the problem of indium shortages. Additionally, economic comparison facilitated by ETSIM is still necessary to evaluate relative costs of the two models. With that, I would like to thank my sponsors, Rio Tinto and Critical Materials Institute, as well as the Kroll Institute, which I've been part of for the last 4 years. And if you have any questions, please let me know.
Thank you, Joe, for your presentation. Just wanted to, yeah, there's a question here in the audience.
So you didn't talk about the application of tellurium or indium, like what they are used for, basically.
Yes, okay, the question is applications of indium and tellurium. So indium, which my work specifically focuses on, is used primarily, pretty much everyone here is within like 3 feet of indium, because it's used in your cell phone screen in indium tin oxide coatings. Around, or the majority of indium goes to make indium tin oxide. So it's a transparent semiconducting layer. Other uses of indium include thin film solar, specifically copper indium gallium diselenide, which is competitive thin film technology compared to cadmium telluride, which makes up about 40% of tellurium usage, is cadmium telluride thin films. Forgive me. Roughly 30% of tellurium is used with bismuth telluride thermoelectric devices, which convert heat into electrical energy. Thank you. That was a good question. Yes.
Yes. Your presentation is very fascinating, and some of us didn't have metallurgy background, for this very nice introduction to some of us. Thank you very much. When you were defining critical minerals, you made mention that they are strategic to security, right?
Could you say it again?
When you were defining critical minerals, nearly the first slide.
Go all the way back.
Yeah.
There we go. Yeah.
Yes, that they're essential to national security. So, in what way does indium essential to national security? That is one. Then, in your conclusion, you were talking about the economic comparison. So, I feel being able to do that because what my mind was going through the entire seminar section, how economical is this process? That was what was going through my mind through the seminar. So these are the 2 questions I have. And Akash has asked my third question.
Okay, so to begin with, it's essential to economic or national security. So indium is more relevant for economic security with its applications. Thin film technologies are more US dominant compared to silicon technologies for photoelectric energy from the sun. So it's importance to that industry that indium has a supply for energy future. Does that make so? It does follow on Akash's question. For the copper indium gallium diselenide, abbreviated to CIGS, C-I-G-S, is a prominent domestic thin film technology. I don't know any specific cases of its pertinence to national security, although screens obviously are, the semiconducting layer is still important. And your second question was economics and comparison of the 2. So obviously ammonia is probably more expensive than water. So that would be a big comparison. It's difficult. So I haven't done the economic analysis yet, but I would love to get back to you with it. There's several other considerations of, you are comparing the economics of the 2 systems, but the one system clearly has benefits over the other. So you have to give value to those benefits beyond just the indium recovery. Unfortunately, I can't really give you a much better answer because I haven't done the economic analysis yet. But the ammonia is also largely regenerated and recovered. So the reagent consumption is drastically reduced. Is there a faster way to do it? So during sulfide precipitation, that regenerates a majority of the ammonia. Some of the acidity consumes ammonia as well, but the pH can be regenerated using lime. So it's an economic consideration, but it's not a good answer to your question. But it was a good question. Thank you.
One, Joseph. So back to the initial point of the critical minerals logic. How is actually critical or subject to interruption is iridium processing or iridium production when Tech, based in Canada, Nearstar, based on Belgium, and Tellurium, based in Missouri, are the major producers in the world.
Who in Missouri?
Tellurium.
Durham? Okay, I'm not familiar with that one, so thank you. Realistically, this work would be done in conjunction with those major producers. So you'd give them partially refined or not semiconductor grade material, and then they would process it further. So they are likely willing to take more feed material as long as it's compatible within their systems. And it wouldn't necessarily be competing with them, it would be working with them. You listed 3 Western countries that are producing indium, but I believe China still produces more than 50% of indium in the world.
That has a lot of
Yes.
from Asian markets, not just China.
Right, so I guess going along with that in critical minerals consideration. It's about increasing options for supply. There's also at least one other smelter, I'm not sure if the third is running right now in the US, that could potentially also use a similar method to slightly increase indium supply.
Maybe not around in other parts other than US because it is banned in several countries because of violations to the environmental laws.
What is?
Tellurium is banned in several countries.
Tellurium?
Violation, yes, to the environmental law. So that may be the reason why.
Okay. Yeah.
Any other question? You?
I have
Yeah.
one question.
Absolutely.
Yeah, you got this indium from copper concentrate, right?
So my material was a flue dust, but yes, it does come in through the ore.
Yeah, okay. How many tons of copper concentrate this as a dust this company produce? Do you have any information about this?
So the numbers I am aware of, I am not going to disclose for Rio Tinto. I don't even think I know anything confidential, but dust is 5 to 10% of the ore feed to the smelter. So the concentrate that enters the smelter, of that concentrate, 5 to 10% reports to dust. That's total dust, not necessarily ESP. The ESP dust is a third of the total flash smelter dusts. Thanks, Nurse.
Any other question here? Just have one for closing. I mean, maybe it's not related with your research, but it's related with the adaptation, the industrial adaptation needed. Do you know something about it? It requires big efforts in terms of design and in terms of construction.
I'm sorry, Leo, could you start over?
Sure. I was asking about the implementation of the technology or the new bullshit, right, to the actual plant. As it requires a lot of effort in terms of industrial adaptation, design, construction. Do you know something about it? I know that's not part of your research, but just.
It would be. So I'm comparing the base case of constructing both flow sheets. If you're talking about modifying existing equipment, obviously that does change the economics and should be considered. Ammonia is not very corrosive to vessels. So that is actually a benefit. It typically does require covered vessels, however, because it forms gas. I'm sure you've all smelled them, hopefully not, but ammonia has a very, very strong smell and will like burn the inside of your nose if you have too much concentrated around it. So sealing vessels that weren't necessarily previously sealed would be a expensive retrofit. Not necessarily extremely expensive compared to buying new equipment, but ventilation is an important factor. Otherwise, a lot of the previously used systems are reused here. I refer to it as a novel flow sheet, but all of the technologies are previously developed. The combination of the different methods is what's novel about this specific method.
Perfect. Okay. Thank you again. Thanks our attendees in the Zoom session. So just a reminder, this record will be available on our YouTube channel. Thank you for coming today. Hope have a good afternoon.